So for introduction, so the building is located in Sultan Abdul Shah campus, Kesash, and it is in between the Faculty of Music and Performing Arts and Aminuddin Baki buildings. So the exact location of this building have been highlighted in figure 1.0. So it houses a collection of artifacts and an exhibition gallery designed to provide valuable insight, particularly to history students. So this resource serves as a platform for enhancing their knowledge and understanding of historical context, equipping them with additional skills and perspectives that are essential for their future role as an educator. So this space is also open for publics who want to plan a visit. So here is the picture of the buildings.
Okay, for the geometrical shape, in this building, we found out that there's a parallelogram, isosceles triangle, trapezoid, and also rectangle. For the measurement, we are using our teammate, which is FEBBIE, as indicator. Her height is 1.58 meter. This shape illustrates fundamental principles such as parallelism, symmetry, and also perpendicularity, which are crucial for understanding partial relationship and architectural design. For the parallelogram, you can see at the yellow line there are the lattice roof sections, which aid in water drainage and provide a balanced symmetrical design. So a parallelogram is a quadrilateral with both pairs of opposite sides are parallel. The properties for the parallelogram are it have opposite angles which are equal. The adjacent angles are supplementary, which is when you add up, it will become 180 degrees. The diagonals bisect each other and divide it into two congruent triangles. The parallelogram law states that the sum of the squares of all sides equals the sum of the squares of the diagonals. The area of a parallelogram is calculated using the formula of area equal to base times width height. Next, in the picture, we can see there's a right trapezoid. You can see at the red line. So a right trapezoid is visible in the front-facing portion of the roof below the isosceles triangle, connecting the roof to the rectangular wall. So a right trapezoid, it has one pair of parallel sides and have two adjacent of right angle, which is 90 degrees. The property of the right trapezoid are it have four sides and also four angles. The adjacent angle sums to 180 degrees. The median is parallel to the bases and divide the non-parallel side equally. The area is calculated using the formula of area equal to 1/2 times in the bracket of A plus B times with H, where the A and B are the parallel side and the H is the height. Next, for the rectangle, you can see in the picture with the green line. So it is the front-facing wall which have the shape of rectangle. It's providing a sturdy surface for the structure. So a rectangle is a quadrilateral with opposite sides, parallel and equal. All the angles are at 90 degrees and the sum of all the interior angles is equal to 360 degrees. The diagonal bisect each other and both diagonals have the same length, which is the area equal to base times width height. Next, for the isosceles triangle, you can see in the picture which have the blue line. So at the top of the structure, the triangular section above the rectangular wall is an isosceles triangle. This shape is defined by two sides of equal length and equal base angle. For the angle sum theorem, where the sum of the angles equals 180 degrees, its area determined by area equal to 1/2 times its base times with height.
For the geometrical concept, we present our building in two-dimensional form, where the line is in a planar state, which only contains length, height, side, base, perimeter, area, and angle. Firstly, for the area, parallelogram show base times with height, which for base, we get 0.16 times with 4.79, in equal, we get 0.78 meter square. For the isosceles triangle, which using the formula 1/2 times with base times with height, each resulting 4.63 after inserting the value of base 7.23 and height 1.28. For the rectangle, which using the formula length times with weight, For the length, we get 3.36, and for the weight, we get 2.72. In equal, we get 9.13. For the trapezoid in area, 1/2 times with in the bracket of A plus B times with height. For A, we get 2.72, and B, we got 2.88, and height in equal to 0.16. And after inserting this value, we get 0.45 meter square. I can continue on the perimeter for the parallelogram. 2 times with the A plus B, 2 times with in the bracket of A plus B, which is A is equal to 0.16 and B is equal to 5.12, which for perimeter for parallelogram we get 10.56 meter. For isosceles triangle, which is 2A plus B, for A we got 3.68 and B is 7.23. After inserting this value, we get 14.59. And continue the triangle. 2 times with in the bracket for A plus B, which for A we get 3.36 and B we get 2.72. After inserting this value, we get 12.16. And lastly for the trapezoid, we sum up all the sides. We get 2.72 plus 2.88 plus 0.16 and plus with 0.18, which resulting 5.94. Okay, for the angle, interior angle, the angle that have 4 edges will proceed to have 360 degrees. While for triangle, which have 3 edges, it will have to have 180 degrees. Okay, continue on the related measurement to the geometrical concept, involve understanding on how physical dimensions such as side angle, length, height relate to theoretical principles. For example, in isosceles triangle, measuring the 2 equal sides and the base angle demonstrate their symmetry and validate the angle sum theorem. For the rectangle and parallelogram, measuring the length, width, and angle illustrate the relationship between opposite side and angle. Calculating the area and the perimeter of this shape in practical scenarios such as determine floor space and surface area reinforce the importance of this geometric formula.
Transformation in motifs and pattern. In this video, we will explore how geometric shape known as motif undergoes transformation that form complex patterns. We focus on one specific transformation, which is reflection. Reflection flips a shape over a line, creating a mirror image of the original shape. The reflected motif maintains its size, shape, and angles but changes its position, appearing on the opposite side of the line of reflection. The first example we look at is the reflection of parallelograms. In the building shown, there are 2 parallelograms, one on the left and one on the right side. These parallelograms are reflection of each other. The line of reflection runs vertically through the center of the building, dividing the left and right side symmetrically. The parallelogram on the left side is reflected over the center line, creating an identical but mirrored parallelogram on the right. The size, angle, and shape remain the same, only the position changes. Next, we have the reflection of right trapezoids. In this case, 2 right trapezoids appear on the building, one on the left and one on the right side. Both trapezoids initially have the same orientation with the right angle at the bottom. However, after reflection, the trapezoid on the right flips horizontally. The longer side switches to the left and the shorter side to the right, but the size and height remain unchanged. The orientation is the main difference, with the trapezoid sides flipped upon reflection. Finally, we have the reflection of rectangles. In this image, we can see a rectangle motif reflected across a vertical axis, running through the center of the line. Unlike the trapezoid example, there are no changes to the rectangle size, shape, or orientation. It simply mirrors across the vertical axis, maintaining the same properties, which creates a symmetric and balanced design. In summary, reflection is a transformation that flips geometric motif over a line of reflection, creating a mirror images while preserving the size, shape, and orientation of the motif. Through the reflection of parallelograms, right trapezoids, and rectangles, we can see how symmetry and balance are achieved in architecture, contributing to the overall design and aesthetic harmony of the structure.
To summarize, the building of the archaeology laboratory is made up of several geometrical shapes, such as parallelogram, isosceles triangle, rectangle, and trapezoid. The building is also found to have transformations in its geometrical shapes, which is mostly reflection, such as reflection of parallelogram that was found on the roof, reflection of the right trapezoid that was found on the pillars, and reflection of rectangle that was found on the wall. To prove that we have labeled each geometrical shape correctly, we have used methods such as calculating the angles and sides needed to prove the characteristics of respective geometrical shapes. Each of these geometrical shapes was calculated carefully by the building's architect and engineers to produce a strong and practical building. Throughout this task, we have learned that geometry is around us, not only used in buildings and structures, but also they can be found in nature too. The knowledge of geometry plays a crucial role in order to create and build strong structures or buildings that benefit us in our daily lives. Take as an example of the building we have chosen. The architect of this building has used geometric principles to design the building, which are not only practical but also aesthetically pleasing. Geometry is not merely just an abstract concept of mathematics. It is an important tool that connects theoretical concepts to practical applications across multiple aspects of our daily lives. Besides, nature itself is actually governed by geometry. If we observe and take a look closely to our surroundings, we could observe that there are patterns of symmetry and geometrical shapes which inspired innovations in designs and technology, where this further illustrates how geometry closely connects the natural world to human invention.